Hi, welcome to lesson 16C, particular values. So in this lesson, what we're going to be doing is we're going to be determining what the value of C is. And interesting how this lesson is in 16C. When we take the antiderivatives and thus are integrating, we always add that value of C, that constant C, because we don't know what that vertical translation might have been for the function. So in this particular lesson, what we're going to do is we're going to now determine what that lesson or what that value of C actually is. Okay, so we'll start out here. We've got dy by dx is given as x minus 2x squared, and it passes through, and the function itself passes through 2, 4. So that dy by dx is the gradient function. So we know that y, oops, I should probably select the pen. There we go. So y is going to be the integral of dy by dx. dx. So it's the integral of the gradient function with respect to x. And then we just substitute that function that we're given in. Okay, we need that dx there for the notation. And then we just find the antiderivatives of each of those terms. So that's going to give us 1/2 x squared minus 2/3 x cubed plus c. And because we're given the point 2, 4, well, that point lies on the curve. So if we substitute those values in for y and for x, we'll be able to then solve for c. So I'll just write these values in. And so that's the x value of 2. And so then, of course, 2 squared is 4, divided by 2 gives us 2 here. The y is 4. And then 2 to the power 3, that would be 8, multiplied by 2 gives us 16/3 plus c. Subtract 2 from both sides, and then I'll add the 16/3 to both sides. So c is going to equal 2 plus 16/3. And then 2, of course, is 6/3. So I'll just continue this up here. So then we get 22/3 as the value of c. So therefore, the equation of the curve itself is y equals 1/2 x squared minus 2/3 x cubed plus 22/3. Okay, and that's basically all you have to do for these types of questions. So we'll move down to example 2 now. Again, we're given the derivative function, root x minus 2 sine x. So the function that we're looking for is the integral of the derivative function. Now, you don't have to write this all the time. I'm just showing this as a first step just to kind of get you familiar with this format. And so it's the integral of, and then that root x I'm going to write as x to the power 1/2 minus 2 sine x dx. And so then we just take the antiderivative of each term, so that we add 1 to that 1/2 exponent, so that becomes 3/2. And of course, we divide by the new exponent, which would be 1/3/2, which then we get the reciprocal of that, so that gives us 2/3. So if you were to differentiate that just to check, you bring the 3/2 down in front. 3/2 times 2/3 will give you 6/6, which is just 1, which is the coefficient that we had initially with that root x. And then we've got minus 2 sine x. So we got the 2 here. Now the antiderivative of sine x is cosine. And when you differentiate cosine, you get a negative. So because we have that negative 2 sine x, the derivative of 2 cosine x would give us negative 2 sine x. So here is going to be a plus. And then we'll add the c. Okay, so that's our f of x. And we're told that f of 0 is negative 2. So if we substitute 0 in for x, we get negative 2 as the y value. And then we've got 2/3. And then the x is 0. And then we're going to have 2 cosine 0 plus c. Now, you will have to have a bit of a working knowledge of what the cosine curve looks like, the general curve. So I'll just jot this down here. So one wavelength of the base function of cosine just looks something like this. Maybe not quite as stretched out, but we'll say this is 2 pi over here. And so that's cosine curve, so then we can kind of pick off the values that we need. And so, of course, we still have negative 2 as the y value. That first term disappears because it's 0. And then 2 cosine of 0, well, cosine of 0 is just 1. So that just gives us 2 plus c. So therefore, c equals negative 4. So therefore, our function is f of x equals 2/3. Now, usually I've said in the past to rewrite the function in the same form as it's given. So it's given in radical form, we can write this in radical form. So that would be the square root of x cubed plus 2 cosine, oops, I missed the 2 cosine x, and then minus 4. I didn't give enough room up there, which I probably should have. If I can slide this stuff over. Whoa. And actually, I'll just rewrite this just to make it look a little bit better. Okay, so there's the function 2/3 root x cubed plus 2 cosine x minus 4. And we'll move on to the last example now. So we want to find f of x, given that f double prime of x equals cosine x. And then we're given the other information about points on the derivative function, the gradient function, and also on the original curve. So if we're given f double prime of x, that means that we're going to have to start with, when we integrate that, we'll first be finding f prime of x. Okay, so we know the integral of f double prime of x will give you f prime of x. So I'll just write this in. So f double prime of x is cosine x. So the integral of that with respect to x. And then so we know that if you integrate cosine x, you'll get sine x plus c, because the derivative of sine x is cosine x. And then so that's going to be our f prime of x. So that's our first derivative. And then we know that when f prime of x is evaluated at pi by 2, the value is 0. So we're going to have 0 here. And then we're going to have sine of 0. And so we also need a general working knowledge of the sine curve. So one wavelength of the sine curve looks like that, and we're looking at pi by 2, so we need pi by 2 marked off here. And we know that that gives us a y value of 1. So we have pi by 2 substituted in for x there. So we've got 0 equals 1 plus c, and therefore c equals negative 1. So f prime of x, the first derivative, is going to equal sine x minus 1. And then the next step, of course, would be to find the function itself. So f of x, actually maybe I'll write this over here. F of x is the integral of f prime of x, and f prime of x is sine x minus 1. So then we'll just integrate this. So the integral of sine x is negative cosine x, and then the integral of negative 1 is negative x plus c. And so that's the original function, f of x. If you just check this, the derivative of cosine x is negative sine x, but sine x is positive, so we have to do negative cosine x. So derivative of negative cosine x would then be negative sine x, which gives you the positive sine x that we were given for this derivative function. And we know information about a point on that curve. So if we substitute in 0, we get the value of 3. So you get negative cosine evaluated at 0. And when we substitute that in, well, negative cosine of 0, well, we know that cosine of 0 from the other example was 1, so that gives us negative 1, and then minus 0 plus c. So then this gives us c equals 4. So the function itself that we're looking for is negative cosine x minus x plus 4. Okay, and that is how you find the constant c when given a gradient function or even a second derivative and a couple other evaluated points on each of the other functions. So that is it for the day. So please enjoy doing a little bit of practice there. And I thank you for watching, and we'll see you in class.